Alright guys, as you can see, I'm going to be absent today. Unfortunately, over the break we had a death in the family, and with funeral stuff going on, that's why I'm going to miss today and tomorrow. But rest assured, I do have notes ready for you guys for the next unit. The next unit involves Extrema. Okay, so it involves Extreme in the sense of absolute max and absolute mins. So what you're going to do today is you're going to watch this video, and it's an introduction into Extrema, and then you have a web assigned assignment as well that is due. So this video in its entirety should at least be viewed, and the questions don't have to be answered. If you want to go back later and slow it down, you can, but they're going to be fairly easy questions. It's a short video, probably like 20 minutes, and then you'll have about maybe 50 minutes or so to complete the assignment, but it has to be done before you leave today. So please do not waste time. Alright, so let f be defined on an interval I containing c. All it says is f is your function. So this is my f function that I just drew. And the interval I means that between this point here and this x value here, I'm evaluating this interval. Okay, so this interval is evaluating the function, which is right here, of f of x, containing c. C is just, we use c because it's going to denote something that is very important, something we call a critical point. Okay, critical point. We'll get to that here in just a sec. It just means something is going on there. It's an absolute max or an absolute min, or a relative max or a relative min. It's when something important is happening in the function itself, changing directions and whatnot, and we'll discuss that here in just a bit. Okay, so f of c is a y value. F of c is the minimum. Okay, so the minimum, it's pretty straightforward as far as knowing what a minimum is. It's the smallest y value, basically. So f of c is a y value. It's the smallest y value on the f function. Okay, so of this f function on that interval I that we were talking about, okay, so this is that interval I, it's saying that f of c is smaller or equal to any other y value, okay, so both of these are y values. It's saying that this f of c right here is the smallest or is equal to another smallest, quote unquote, y value for all the x's in that interval I. Okay, so it goes pretty straightforward, okay? F of c here, it's a y value, is the maximum of this function that I have on an interval if that y value, and those are the same, is the biggest or equal to the biggest of all other y values that are in that interval. Okay, so the minimum and maximum of a function on an interval are the extreme values, or extrema, okay, extrema for plural, of the function on the interval. The minimum and maximum of a function on an interval are also called the absolute. Okay, so the absolute max, the absolute min, otherwise we can also call them a global minimum or a global max. So absolute and global being synonymous, meaning the same thing. And why are we trying to minimize or maximize functions? Because in real world application, we're trying to do things, for instance, minimize cost. You know, if we're in charge of a big corporation or big company, we definitely want to minimize cost so that we can maximize profit. Okay, so these are just the small little things. You know, if I'm a doctor and I'm trying to do surgery and I'm analyzing the growth rate of the like cancer cells and whatnot, I want to minimize the growth rate and maybe maximize the counter attack or the countermeasures that I'm able to use to prevent it from growing or to prevent it from spreading. So there are many different ways that we're trying to basically incorporate derivatives by analyzing how does it minimize something or how does it maximize something else, whatever benefit is needed at the time. So, okay, so the definition of relative extrema. Okay, so relative extrema is a little bit different because over here, this said that there were y values and it'll be the biggest y value or the smallest y value depending on what you're looking at. And this is for the key is for all x's in a certain interval. So a certain interval domain. The difference here is when I'm looking at relative extrema, I'm not looking for all. Okay, it's not looking for across all x's in the entire interval. It's looking for some x's in a small or smaller interval I. Okay, so for instance, if I had a graph that looked like this, I would say that if I'm looking for relative, which is the same as local, look, let me come over here, relative min, relative maximum, relative maximum. Over here I have a local maximum and local minimum. So if you see absolute, like we talked about ahead or above, it's the same as global. Or if you see something that says relative, it's going to be the same as local in the immediate surrounding area. So for instance, if I were to come over here and highlight in purple, I could say that this right here is a relative, i.e. a local maximum. It's not the absolute, because if I'm looking out on a bigger interval, this would be the absolute. Okay? So let's say that I was only analyzing on the interval, and I'll draw it in, let's say, blue. If I was only analyzing, and this is my x-axis, if I was only analyzing, let me pick a different color, this interval right here, then what is in purple would be not only a relative minimum, but it would be the absolute, a relative maximum. It would also be the absolute maximum in that interval from A to B. But what if I extended the A to B and I said, this time I want to look at from A to B, being from here to here. So from A all the way to this B. So my interval now has changed. So if it's from here to here, I have, let me highlight in red this time, this is going to be only a relative maximum. It's not going to be the absolute because of the fact that I have an absolute maximum over here. So that shows the subtle change. Relative is local and the absolute is non-local. It's basically same for the entire interval. So again, if I have just one vertex, like a parabola, maximum written here, and I'm looking from A to B, well, of course, this is relative and maximum. And we'll get to that here in just a bit with other examples so that you can see it a little bit clearer. I just want you to understand the difference between absolute and global versus relative and local. So let's keep reading the definition of relative extrema. If there is an open interval containing C on which f of C, so this is a y value, is a maximum, then that y value itself is called the relative maximum. The difference is that this is saying on a smaller interval, if you will, and it's an open interval. Okay, this is closed, this is open. Okay, so absolute would be on a closed interval, where the relative min or the relative max would be on an open interval. Okay, so it says then that y value is called a relative maximum for f. Or you can say that f has a relative maximum at this point. This is like an xy coordinate, if you will. Okay? If there's an open interval containing C, okay, so there's an open interval that has an x value, where that y value evaluated at C is a minimum, then that y value is called a relative minimum. And you can say that f has a relative minimum at that xy coordinate point. Okay, so what is it that we're looking at? We're looking at, again, relative maximum and relative minimum, and how they're synonymous with local maximum and local minimum as far as this open interval here. Okay, so the big thing that I want you to get is the fact that you have closed, which are absolute, and open, which are relative. So let's try to break it down and see picture-wise what we're talking about. In the figure on the right, on the closed interval, okay, so already we're looking at a closed interval. From -2 to 4, these are x values. Let me highlight it with a different color. These are x values. It's saying from -2, which is about right here, all the way to 4, we're evaluating this closed interval. F has an absolute maximum where? Well, if I'm looking at this, I know that I reach some kind of maximum here because I have stuff going down and I have stuff going down on both sides at this point, but it's not the actual absolute. The actual absolute maximum is the biggest y value in the entire interval from -2 to 4. So in this green interval from -2 to 4, my biggest y value ever is going to be accomplished here at 21. So f has an absolute maximum at, you could say, x is equal to 4. Or if you want to put 421, you can. But one thing that I want you to be very, very clear about right off the bat is, if I ask you where is it at, it's talking about the x value. If I asked you what is the max or what is the min, that's talking about the y value. Okay, so the difference between what is it and where is it at. Okay, so what is it would be that y value of 21, and where is it at would be at the x value of 4. Okay, so f has an absolute minimum at, so all these have at. So I'm going to go ahead and now erase this, because the only answer that you should be writing, since the way it asked you, is that x is equal to 4. Okay, so we could say f has an absolute minimum at, well, from -2 to 4, my lowest y value is -15. But it said, where is it at? So I'm going to put at x is equal to -2. F has a relative maximum. Okay, so this is that relative maximum that we were talking about earlier. Well, where does it occur at? It occurs when x is equal to 0. So that's what my at value is going to be. And then finally, f has a relative minimum. Okay, so here's a relative minimum. It's not the absolute, because we already denoted that at being at -2 with a y value of -15. But we're saying relative. Basically, these are relative or local. And then these, right here and here, put some arrows, are absolute. Okay, so let's go over here and finish what we have. F has a relative minimum at x is equal to 2. And that's talking about that point here. It's not absolute again, it's just relative because it's in the immediate surrounding area. It's the local. So definition of a critical number and a critical point. So this is basically, in a nutshell, why this unit is so important, because it's looking at max and mins, and it's looking at critical changes that occur. So critical numbers, right off the bat, what I want you to know is when its derivative is set equal to 0. Okay? So if f is the function, and I derive it, and I set it equal to 0, and I solve for when this derivative would equal 0, we call that a critical point. So critical points occur when the derivative is equal to 0, or if it's non-differentiable. Okay? Basically that I can't take the derivative. Okay? So then C is called a critical number. So when I can take the derivative and it's equal to 0, or when the derivative is equal to undefined. So critical numbers is when f prime of c or f prime of x is equal to undefined, or, so it's both of these, when the derivative is equal to 0. So relative extrema occur only at critical numbers. So relative are the locals. So if you analyze what this is saying, if I drew some sort of tangent here, that tangent's value is 0 because it's a horizontal line. If I drew a tangent here, that would also be 0. Those are relative. And it says relative extrema occur only at critical numbers. Whereas absolute, if you look over here, I can't take the tangent of an endpoint. We've discussed this way, way long ago. Remember, you can only take it whenever the limit exists. And you have basically wings to a point, if you will. And when I say wings, I'm saying like a bird. So you have things that are coming from both sides. It's got local linearity is what it's called. And that it's slow and it's smooth and it's a curve that basically you can derive and take a derivative off. Like you would say the derivative is right there. Something that I can't take the derivative of, an example that we've looked at, is like an absolute value function. Now I know it's been a while, I know we've been on Thanksgiving break, but an absolute value function, we can't take the derivative because it has a cusp. And that would fall under the undifferentiable part. Either way, this is a critical number because the slope is 0. This relative max over here is a critical number because the slope is 0. And this would be a, at this x value, would be a critical number as well because of the fact that I cannot take the derivative. So when do the undifferentiable parts happen? At cusps, at vertical tangents, jump discontinuities, infinite discontinuities. So vertical tangents, jump discontinuities, and infinite discontinuities. And then the last thing that you cannot take a derivative and that it would be undefined, we're going to add to it right now, are endpoints. Because you'll see a lot of that in this, those examples in this unit. So in the following examples, name the maximum and minimum points. So now we're going for the points, if possible. So minimum at where? Well, if I'm looking at this, this right here is looking at the minimum. And if I'm saying where is the minimum at, we're going to say at x is equal to 0. Now, because it's saying points, we're also going to go further and say this point is 0, 1. Okay? Because that's that y value right there. Or you could write it as f of 0 is equal to 1. Okay, so two different ways to write a point, if you will. xy that you're used to since algebra 1, or you could say f of 0 is equal to 1. I would say this is more preferred because it's really understanding the fact that you know the minimum value is 1 and it occurs at, so is 1 occurring at 0. Okay, so minimum, or sorry, maximum on this one. Well, what is the maximum that you see? It is a closed interval because you see these are colored in, so it is a closed interval. So its maximum point will be right here, whatever that is. So we're going to say at x is equal to 0, or sorry, not 0, 2. And specifically the point would be 2, 1, 2, 3, 4, 5. So 2, 5 is the point. Or f of 2 is equal to 5. Okay, so let's look at our second example. Our second example is closed on the left, but it's open here on the right. So what is the minimum? The minimum will occur still at x is equal to 0, right here. It's still 0, 1 as far as a point, otherwise known as f of 0 is equal to 1. So the minimum equals 1 occurring at x is equal to 0. Okay, I want you to understand the subtleties in that because depending on how the question is asked, you'll have to answer certain ways. The maximum is not going to be at x is equal to 2 because of the fact that this infinitely will approach as x approaches. It's almost like a limit. As x is approaching 2, the y is approaching that value of 5 that we talked about over here in this other example. But because the fact it actually never hits it, we cannot say, and it's not closed, okay? It's not closed, it's open. We cannot say that it would be 5. So this would be not possible. So let's put not possible. So let's look at our next example. What is the minimum? The minimum is not possible here. Okay? And the minimum is not possible because of the same reason. It's infinitely approaching x is equal to 0. And as x is approaching 0, the y's are infinitely approaching 1. But they will actually never hit 1. Because it's infinite and it goes on forever and ever and ever, wanting to approach 1 but actually never hitting it. We view it as a non-quantifiable endpoint. Basically that open endpoint. So that's why it's not possible of having an actual. So these are actual quantifiable. So we'll say actual quantifiable minimums. So it's not possible. The maximum would again be possible. And we would say at x is equal to 2, otherwise 2, 5, otherwise f of 2 is equal to 5. What conditions are necessary to guarantee that there will be a maximum and a minimum? Okay, so the conditions are it has to be a closed interval. And as far as, well, we know it has to be a continuous function. That just goes without saying. And that's pretty much it. The big things is that it has to be closed for it to guarantee that there will be a maximum or there will be a minimum. It has to be defined. Basically, no jump discontinuities, no open holes, no things of that nature if you're looking at certain intervals. Okay, so now let's go to our next slide. It says Extrema on, hold on just a bit. So let me insert right here because I did reduce your assignment because of time. And it's basically going to look at this. If I have a graph, and the graph looks something like this. Let's look at A, B, C. This right here lined up perfectly with both this open and closed will be D. And let's say on A to B, and we'll put it to where it's closed and open. Does there exist an absolute max? Well, there does. Right there. That is the absolute max. The y value is the absolute max. Where does it exist would be the x value. Now, what if I said, where's the relative max? Would it be the same? Yes. In this example, the relative or the relative max can also be called the absolute max. Because I'm only looking on this interval. Now, if I said for the entire interval from A to infinity, then that would not work. It could be a relative max because its surroundingness goes down on both sides, almost like the wings of a bird, if you will. But it would not be the absolute because this one is a little higher. So it would be the absolute if I said its new interval I is A to infinity. So it definitely depends on what I or what interval you're evaluating to see what you're going to denote it as, a relative max or a relative min. Okay? Now, let's say that this function gave me f of x was equal to, and this is not the function, but let's say that I have another function, 3x squared minus 4x. And I want to say, where is the max and min on that function? Okay? The max and min on that function will occur either at the endpoints, so at A or B, or it occurs somewhere in between that we're going to call C. So at a C value, where when I take the derivative, it is equal to 0 or it is equal to undefined. Okay? So it's going to be one of those two. It's either going to be 0 or undefined is where a relative max or a relative min would occur. Or we could say it could be at the endpoint. So what we're analyzing here, and you'll see with the homework here in just a bit when you start your WebAssign after this slide, you're looking to analyze if the derivative is equal to 0, it could be a max of either absolute or relative. If the derivative is equal to undefined, it could also be a max of absolute or relative. So let me write that like this. Absolute or relative would be here when the derivative is equal to 0, when the derivative is undefined. As far as being only absolute, this could also occur when the derivative is undefined, or 0, or the last part, an endpoint. For instance, if I had a graph that looked like this, because the derivative is undefined at this particular x value right here, so let's say this is my xy axis, and I'm looking at this particular c value right here, the derivative here is non-existent because it's an endpoint. So this has the capability of being an absolute max or an absolute min, not a relative. Okay? So, like I was saying back here, this can be a relative max because of the fact that that derivative is equal to 0. So if I had an inverted absolute value function, the derivative here is undefined. That could also be a relative max because of the fact that the derivative at this particular c value is undefined. It's a cusp. Okay? So if I had a graph that looked like this one right here, this absolute value function, this particular example, if it went like this forever and like this forever, I could say that this is not only a relative max because it's undifferentiable, it's also going to be an absolute because there are no other y values that are bigger than that y value anywhere on this interval that I'm looking at, if it's going from negative infinity to positive infinity. As you do more and more of the examples in the homework, I think you'll understand more the differences between absolute versus relative. Alright, so I will see you guys on Wednesday.